Hey guys, welcome to RET-211. Today what we're going to do is we're going to go through our RET-200 document to be able to just do a little bit of our intro. It's been 6 months to a year since the last time that we talked about residential solar, so this is a good time to go into it. So with our last RET-200, we went into residential solar, so we're going to start there. A good portion of our business and solar still is with rooftop solar, so it's a good place to start. We are moving into doing a lot more commercial and a lot more utility grade installations, especially now with the COVID, because people don't want you to come to their houses when there's a pandemic around. Imagine that. But commercial scale solar and utility grade solar is still going on, and it will continue to be residential as we move forward through this. But we're in a weird period of time, so I just thought I would go through some of the documents here. I did post a lot of resources here that I'm not going to go into on manufacturing of solar. And it goes through the other things of how is solar made, how is solar designed, how do we dope it, and then how do we manufacture it. And then also I have a cool one from 2020 here on what the most efficient solar panels are. So if you get a chance, go ahead and check those out. I think it's under lecture resources, so and there's a bunch of YouTube videos there. It will also go through what the solar window is and how direct energy is covered at a 90-degree angle with that flashlight theory. So if you don't have a chance, go ahead and check out that Schoolhouse what is the solar window video also. But I'll cover it here a little bit, but if you want more detail, there's a 10-minute video that describes all of the how is solar done. So check those out after this. Okay, so the solar basics of residential design. Solar is amazing, but how much does it cost, right? So we all love solar. Solar's super great. So let's go into some of the nuts and bolts here. Okay, so people say, I want it. And you're like, okay, hold on. You don't even know what we're doing here. Why don't you tell? They just want to know right off the bat when you're talking about solar. They just want to know the costs. And they're still thinking back in 2019, 1999, and back then when they're like, which it doesn't sound like a long time ago, but that was 20 years ago, guys, where people said solar's just too much. And it's like, man, the incentives out right now are so good, especially if you have moderate to low income, that you probably can afford this. And even if you don't, most of the solar programs with financing are zero down, and the cost of your solar payment is less than the electricity you're paying. So as far as the payoff goes, I mean, it doesn't necessarily, it does matter, but it doesn't matter a lot, because if you're paying, let's say, $100 a month and your payment is $80 a month, you're still saving $20 a month, even if it takes you 15 years to pay it off. And that's considering that PGE never will increase the cost of their energy, which, they do. They have increased it pretty consistently over the life of the 20 years that we've been doing this. Sometimes it's lower, sometimes it's higher, but it averages, that goes up. So with us, we're not so much worried about what the cost is. I'm going to tell you about what the systems are and how they work, but we will go into the cost also. So the good question is, well, what are we trying to achieve? Are we trying to do grid-tied solar? Are we trying to have energy independence where you never have to pay a bill again? Do you want to have off-grid systems? Are we trying to do just battery backup? So let's take a look at what some of these are. So first off, we have solar PV. That's a grid-tied system. So this is about 95 to 98% of the systems. Then we have these new ones coming out called grid-tied backup systems, which is like your Tesla walls and your custom battery systems. We call those AC coupled systems. And then we have off-grid energy dependent, which is a DC coupled battery backup system, which is the traditional battery backup system that has your modules, a solar charge controller, batteries, inverter, and then your essential load panel. as we go through here, so this is our simplest system that we have. This is the batteryless system. So we have here, we have our PV system, we have our modules, and then we have our DC disconnect, we have the inverter, we have the AC disconnect, and then we have our breaker panel. Now, sometimes in different jurisdictions, you may or may not have this additional AC disconnect system, and this system also may not have a separate inverter. Traditionally, we would use this with a string inverter, or possibly even a one that uses DC optimizers on it. But we do also have microinverter systems that have the inverters built into each one of these modules. And if you guys remember, for RET-211, these modules are consisted of little tiny cells. So each one of these, we'll go into this more when we go into the system components next week. But as we go through here, each one of these cells, roughly about half a volt in monocrystalline and polycrystalline, and they're tied in series with each other. So a 60 cell system would roughly have around 30 volts, and a 72 cell system would have around 36 volts. Open closed circuit, and then open circuit voltage would be 0.6. So whatever 0.6 times 72 or 60 would be, that's your open circuit voltage for those. That's with it disconnected. And then what we do is we tie each one of those series circuits in line with each other. So series circuits add the voltage. So in this case, let's say we're at 36 volts and we go here, that'd be 72 volts, and then we would go up and we'd go up and we'd go up. And then by the time we do that, all of these panels are hooked in series with each other. And so they would be at roughly about 400 to 500 volts usually, let's say high 300s to under 600. Now we do have a regulation that we can only get systems on residential systems only up to 600 volts. And so we're regulated due to the NEC at that. Most hardware can handle up to 1,000 volts, and there is some headway in different jurisdictions to get up to 1,000 volts, but mostly that's for commercial systems. And then, so that's for your traditional DC optimizer system, which we'll get into later, and a string inverter system, which makes sense because they're in a string, they're in series with each other. But there is, with microinverters, it's still hooked up in a very similar way physically, but instead of being hooked in series, they're being hooked in parallel. So all of your voltages are at 220 volts, or 240, and your amperage is what's getting pushed up, and you would eliminate this guy here. Now sometimes the jurisdiction may or may not have an AC disconnect system because it just depends on jurisdiction. Sometimes they want an AC disconnect so that the utility workers or somebody can come out and they can disconnect your system if there's an issue where it goes down on the grid, and other people say we can do that remotely, and we're going to turn that off anyways through on our junction boxes, so we don't really care. So you can just use the breaker. Okay, so the originalist system, I think I'm going to skip this for a second because it's a lot more complicated. So we're going to go to the off-grid system. So the off-grid system is not connected to the grid. So in an off-grid system, we have our PV modules, which goes to a charge controller. The charge controller charges up some batteries, and then it goes into a sunny island, or goes into an inverter. It doesn't have to be a sunny island. And then it goes into your breaker and then powers your house. So this system's completely disconnected from the grid. And unfortunately, because it is disconnected from the grid, you get zero incentives for this system, which means it becomes a whole lot more expensive later on. Kind of a bummer there. Big bummer, actually, but that's how it works. Now, there is some interesting things here, is that the PV modules, depending on what kind of charge controller, could be a grid, the ones we use for grid-tied systems, or they may actually be smaller modules that work at lower voltages. So you may be working with 24 volt I'm sorry, but 24 cell systems, which would give you 12 volts if they're really tiny systems, or you could be working with 36 cell systems, which would give you 18, or you may be working with 72 to give you 36. But so you can. You may have different modules that are being used here, but most of the charge controllers now are standard, and they can work within the voltage requirements that's needed for standard solar cells. But you may run into that. So if you are building an off-grid system, you need to make sure that you look at the charge controllers minimum and maximum voltage requirements, because it may run into an issue there. The same thing with the amperage. Okay, so what is the difference if we look at this system versus this system? Well, the big one that we notice here is we have this. We have a DC charge controller, and we have a sunny island. Because before, essentially, we have PV modules, goes into a sunny island, into a breaker, AC loads, and then the other difference is that it goes out to the grid. So these two pieces are the things that cause a lot of the big issue here. Now, you would think that you should just be able to use the same inverter, but the inverter, if it was a string inverter, is actually designed to be able to run at somewhere between 300 and 600 volts, while this is only a 48 volt battery backup system. If you're using lead acid batteries and you have 4 batteries in series with each other, 12 volts apiece, or potentially even 8 batteries in series if they're 8 cells, 6 cells, 6 volts apiece, 6 times 8 would give us 48 also. So you may have a 8 series system or a 4 series system to give us 48 volts, and the input and output of your inverter is going to run at one of those voltages if you're doing lead acid batteries. And we do have cadmium batteries, and we have nickel hydride batteries, which almost never gets used because it's just too expensive and the duty cycles just isn't there to justify it. But now we have electric cars coming out, and we have lithium ion that's coming in, and they run traditionally per cell voltage is about 3.7 volts, and they come in lots and lots of different voltage sizes, and so the inverters are now able to handle lithium ion systems, and they could potentially be in the realm of a standard inverter, which would be great because they're a lot cheaper than the battery backup inverters are. Because you have higher voltages, which means you have lower amperages for the same amount of power that's going through. Again, we'll cover it more. I'm just going into the nitty-gritty. The DC charge controller here is going to run off of the input to the voltage here, and it's going to also have an input voltage to control what it's charging on the side. You need to make sure that you match your DC charge controller to what your batteries are. Don't get a lead acid battery charge controller for a lithium ion system, because it could cause them to catch on fire, which would be really bad. So we do have a couple of pieces here that we have to work. So then somebody said, not somebody, but everybody pretty much when they get solars, they say, well, why would I want to have a battery backup system on my grid-tied system? Because when the power goes out, I'm still going to be able to run. Unfortunately, that's not true. Our grid-tied systems are designed to protect linemen that are working on our service lines, and so we have this system called anti-islanding. We want to make sure that our power system doesn't become an island by supplying electrical power to the grid when linemen are there to try to fix the power lines. So what we do is we actually, by law, our grid-tied inverters turn off if the power goes off. So what that means for you is that if the power goes out, you can't get your power because the grid is off. And there's a sensor in there that monitors the electrical, it monitors the grid, that it's at 240 240 volts at 60 hertz. It has to be super stable, and if it doesn't get that for 5 minutes, it just shuts off. Well, actually, if it doesn't get that at all instantly, it will turn off, but it has to get it for 5 minutes to be able to turn it back on. So then this is a problem, right? So now we have our Tesla walls coming out. We have these other things where people say, well, actually, you can get battery backup at your house, and we can create an island if we turn off this main service panel. So now what we've done is we create a new system that is a hybrid of both the off-grid system and the grid-tied system. So what we do here is we have our PV system. We have our grid-tied inverter. That's the AC main panel. That's the original system right there. And then we have this battery-based inverter, a generator, a battery bank, and a DC load panel. What does that look like? Well, that's the grid-tied system, right? Or the off-grid system. So this battery-based inverter, what this actually is this is a inverter / charge controller. So this is really a charge controller that has a built-in inverter inside of it. And it can flow either directions, right? And so you could get 2 individual parts to be able to do that, or you could use one and get this thing going. So so a lot of times what they do is the PV system, when it's grid tied, it's going to go through here and it's going to charge that battery bank. So first off, it's going to charge anything in your house, then it's going to charge the battery bank, and then it's going to supply the remaining energy will go out to the grid and give you your credits that you need for your net metering. Then once that battery bank is filled up, what should happen is the grid goes down. And there is a automatic transfer switch that is built into the inverter sometimes, or it's a separate unit that is tied into the battery bank. And what it does is it switches the power from your service panel over to the battery bank. Now you'll notice that there's this DC load panel, which is like, you will likely not use that. But what that is there's a lot of people that say, hey, if I'm inverting and rectifying, I'm going to lose, 2-3% energy every time that I do that, and I could lose 6% of my energy. And, if I'm talking about 20 amps, that could be a significant amount. So there's a sect of people that want to run their like DC lighting and DC refrigeration and all this kind of stuff to save that 3%. Personally, I think it's a lot of extra that you don't need to do. So I would just, if this was my system, I would kill that DC load panel because I don't think it's necessary. But I would probably create a new AC service panel. So what that means is I would create a AC panel. There's your standard panel. Then I would run what would be called an essential load panel. And so that would hold your things like your refrigerator. It would do your lighting. It could do your washing machine, things that that you really need for your living. Could have your TV on it, but it may take off things like having your shop connected where you're going to be pulling 60 amps. Unless you own a wood shop and that's how you make your money, then that could be essential to you. But for most people, you can eliminate, probably 2/3 of everyone's electrical needs, based on just what they actually need. What that does for you is it allows you to be able to create a smaller battery bank, which saves you a lot more money if you're not powering the whole house all the time, or at least, having to power the whole house at the same time. So then what we do is the automatic transfer switch turns that off, and then now you are able to create your energy on your home. You have your backup energy. And as long as your battery bank is large enough, the solar system continues to charge it up. You can stay off grid that whole time. And then if the grid comes back on, hey, no problem. It kicks back on, everything works. Automatic transfer switch turns back, charges your battery, and everything works like normal. They are significantly more expensive. Could be 2 to 3 times the cost of what your existing grid-tied system is, because there's a lot more complexity, but that's how it is. This generator here is kind of an interesting option. So the reason why the generator is there is to be able to create a fake grid for you. It's really its only purpose. It's just there to be able to turn on for 5-10 minutes to be able to turn on your existing system. Because what will happen is the automatic transfer switch will turn off, the grid will turn off, and then you still need a signal from the grid to be able to turn on this grid tied inverter. And since it's way up in the chain, it's going to need to see that. And so what the generator does is it produces a sine, what's the term here I'm looking for? It's going to create a clean signal for the 60 hertz that it's needing for the grid. And then once it gets that for 5 minutes, it'll kick on that inverter, which will turn on the battery-based inverter, and everybody will be happy and it will run. You can turn off your generator, and now you're running on solar. So the generator could be gas, could be propane, could be hydrogen, could be gasoline, could be diesel. It could even be a small little battery, a battery that is designed to be able to just be that thing for 5 minutes. So it could be just a golf cart battery that has a little MPPT charge controller and inverter on there, and that's what's being used to be able to power up your inverter. So there's some options there. It doesn't have to be a physical generator, but it needs to be something that can provide that that grid tied connection. Okay, so now we're going into the bigger stuff. Okay, so we know how solar is installed in general, and we're going to go through the components. So if you didn't get all that, next week we're going to go through each one of those and spend some detail. Here is our solar resource map. So we have the average daily radiation or insolation that we're using, and we have this this measurement called a sun, which is a kilowatt per meter squared per day. And on our solar panels, we have our solar panels are rated at this too with our STC. So you'll notice here in Portland, Oregon, we are in the 0 to 2 rating. We're actually pretty much right at 2, depending on the coldest month. We can go down to 1.9 for our for the amount of light that we're getting. There are some days that there was a few days last year where we actually got 0.9. So we actually got less than 1, which is pretty incredible. But it only lasts for, a day, and then it's back to normal at 2. And then during the summer, you'll see we are over here. We look at Portland, Oregon again. Where's my mouse? Whoop. And we're in the 5 to 6. So in Portland, Oregon, we range somewhere between 2 and 6 throughout the whole year. And so what that does is that averages out at about 4. And that looks like that tracks also. And you can see where it is all over the state. So you'll look here, it looks like in Arizona, we're at about 7 to 8, which is pretty impressive. That means that they would get a lot more light than us. And so the same solar system would provide more energy. So let's do some basic math on that. So let's say that you have a solar system, and it's a 10 kilowatt solar system, because the math on that is really easy. So let's say that it has 10 kilowatts, and that is the peak rating. And annually, we want to find out how much energy that thing is producing in Oregon, or in Portland, Oregon. Well, we would take the 10 kilowatts, we'd multiply it times the 4 suns, and we would get 40 kilowatt hours per day is what that system is able to do. And then during the winter months, we could get an average of around 20 kilowatts, because it would be 10 times 2 suns. And then during the summer months, we would get 60 kilowatt hours, because it would be 10 kilowatts times 6 hours of sun to give us 60 kilowatt hours. And so on average, it's going to give us roughly about 40 kilowatt hours. And on some days, we may get 7 kilowatt hours or 70 kilowatt hours. And on some days, we may get 10 kilowatt hours. So it kind of depends on how much light we're getting, how much clouds we're getting on that time, and all that kind of stuff, right? So when we're doing a grid-tied system, why this is important is because we can pretty much just go off the average. We're going to get a credit based on net metering. So what we can do is we're going to overproduce during the summer. We're going to underproduce during the winter, but the summer's production will make up, even though it's only 3 months, it will actually make up for the winter's reduction. And so we'll be within a few dollars of what the credit is. You may have to pay a couple bucks, or you may make a little bit extra, and then any remaining credit that you make, at least with PGE, Portland General Electric, will get credited to someone who can't afford electricity. So you're also doing something good there. There's actually some people that purposely build bigger systems because they want to use that as a credit to be able to help other people out, and that's a great thing. So on a off-grid system, it's completely different. An off-grid system, you have no... The grid is kind of acting as like an extra battery for you that you don't have to pay for. So with an off-grid system, you have to provide all of the energy for yourself. So what that means is that you have to choose the worst day of the year, or at least if you have a couple of days where it's not going to work, then that's okay. But it's probably better to budget for those 0.9 suns versus the 2 suns, but at least budget for the 2 suns for building your battery bank, and then you'll be able to float that. So again, if we had a 10 kilowatt system and we were able to do 1 sun, that would be 10 kilowatt hours. So as long as your house was able to do 10 kilowatt hours or use 10 kilowatt hours, by the time the sun came back up and was producing energy at, let's say, 8 or 9 in the morning, and it technically produces at 6, but 8 or 9 in the morning is a good metric for you. Then from when the sun goes down, let's say if it's in the winter, it could be 5 o'clock. So from 5 p.m. to about 8 a.m., if you use less than 10 kilowatt hours, then that system will work. If you don't, what you have to do is you have to build a bigger battery bank to be able to store that energy, so that when you do have more energy during the day, it will charge into that battery bank and give you more supply. Or you may have to have a larger PV system to be able to give enough charging capacity and enough storing capacity. And what that means is a lot of money. A lot of money. These systems could be in the $60,000 to $60,000, $80,000 range, just because of the batteries. Batteries are expensive. With the cost of lithium ion coming down, especially with electric cars coming down, I'm really excited to see how that's going to happen. There's a lot of people who are taking wrecked Nissan Leafs and converting them into low-cost battery options because they're able to get 24 kilowatt hours, and the car only costs like $3,000 when it's wrecked. So that's an incredible deal. You saw my eyes go all crazy here, but it's a really good deal. I want to say that when I bought my 9 kilowatt lead acid system, it cost it was like, let's see, I bought 8 batteries, and 8 batteries were roughly like $300 and maybe $300 or $400 a piece. So that's 4 times 8 would be like $3,200. Yeah, so I bought a lead acid system which has less charge cycles. I mean, it's pretty durable, but so $3,200, maybe $3,500 for 9 kilowatts. And with this, you can get 24 kilowatts that has more energy production, and it would simplify the system and has better voltages and all that kind of stuff. And your hardware in general could be cheaper, and you could get it for $3,000. So that's very, very exciting. Okay, so I hope that that all makes sense. We're going to go into the cost now. So, how much does it cost to do a grid-tied system if I just want to save money? Okay, so first we need to decide the system. Is it the hottest month, the coldest month, or annually? We just talked about it's a grid-tied system, so we could do annually. If it was a off-grid system, it would be the coldest month, right? Or the one, not necessarily the coldest, but the one that has the least light. And then how much electricity do you want to use? And okay, well, let's say that I use 600 kilowatts a month and I want to offset 100%. Well, this isn't ideal for the payback, but we're going to show why. Remember that 4 kilowatt hours is the annual, 4 suns, and 1 sun is equal to 1,000 watts per meter squared at 25 C for STC. And so we take our monthly usage and we divide it into the days, and we divide the number of suns into the days. So a 600 kilowatt system divided by 30 days in a month gives us roughly about 20 kilowatt hours a day that needs to be done. And then we divide that into 4, and we get a 5 kilowatt system. Oops. Aha. I should have read my script. Then we take this, you'll see why in a sec, and we take this measurement and we calculate a 5 kilowatt system, that they're not 100% efficient, and so we need to find out how many panels we need. So we take our 5,000 watts, we divide them into some 300 watt Solar World panels. This slide is a little old. Solar World doesn't exist anymore, unfortunately. With string systems, they have to be balanced. So they either have to be in even amounts. So we can do a 16 or we can do an 18. Technically, we could do a 17 if we were doing microinverters on there. So this is going to be, let's choose 16. So then they're all in series. They'd be 32 volts at 16 panels. That'll give us 512 volts, or 576, which is under the 600 volts. So we could do either. Doesn't matter. Then we do the breakdown of the costs here. So I updated the costs, but I updated it for a 6 kilowatt system. So the costs are actually a little bit more here. I apologize because I didn't read my slide earlier. But so we have our PV modules here. These are all 2020 prices as of April 12th, I think it is today. I'm not sure. $6,980 for the PV and the racking. The combiner boxes and the wiring is roughly about $800. The inverter's $2,350. That was for microinverters for that, or a string inverter. They're roughly about the same price. And then the labor for that is roughly about 50% of your costs. Or it's the same price as what the hardware cost is a lot of times. So about $7,500, and that comes out to about $18,000. Could be up to $20,000 depending on if the labor is a little bit more for this. And we'll talk about the labor here in a second. So if we want to save our monies, we have our PV modules. That's $6,980. Combiner $800. Wiring $800. Inverter $2,350. Labor $7,500. Gives us a cost of $18,430. And so that's the hard cost of the system. Then what we do is the ETO has changed. It used to be at 50 cents. Well, it used to be at $1.50, then $1, then 90 cents, then 80 cents. Then, as the cost of solar comes down, the cost of the incentive comes down also, so that they can provide more for everybody. Because we got some really weird things that happened, maybe 10 years ago. Oh God, it's going on 15 years ago now, where people are getting paid to be able to put solar on their roof, and it was just an unfeasible system. But it also got to the point where it's like, if you paid $1,000, you could get a solar system, and so what's interesting about that is they've released another thing in this next slide that's real close to that. So right now though, if you just look at the ETO incentive, you get 30 cents per watt. And since I spec'd it for a 5,680 watt system, that would give you $1,704 back from Energy Trust of Oregon. The state doesn't have any funding for that. And then we have the federal tax credit, unfortunately, went down from 30% down to 26%, and will go down at the end of this year, down to 22%, I believe. I'll have to look into that. And then it's gone. So hopefully we get some new administration in here that will bring that solar system up, because it's been shown that the investing in solar and renewables infuses, for every dollar that they give us, it infuses $5 into the economy, and in some regions $10 into the economy. So it's makes a lot of money and helps their tax base, because people have to get hired, and people have to go to school, and people have to get licenses and things to people install the solar, and that all helps the economy. So so the total system is 1840. We get 1704 from ETO. We don't get anything from the state with this incentive, and then we get 4349 from the Fed, and so our total system is $12,377. So what is the payoff on that? Well, we save roughly about $856. Could be a little bit more for this size system, maybe up to $1,000, but I estimated about $856 through through the home, the solar on my home, and so that is about 4.5 years at current PGE rates, and that could go up and down. Now, the thing that we were talking about before is that if you're paying zero down and you're also paying less for your electricity, the payoff may not matter to you, because what's the payoff for being hooked to PGE? Infinite, right? Like, you're never going to pay off PGE. They don't. This isn't a lease program. You are renting their grid, and you'll never pay it off. So at least, hey, 4.5 years, you'll be able to get that, and you'll actually gain value. So one of the things that a lot of people question is, what is the value of solar on your house? Well, in 2010, there was a study that was done for 6 years that the Energy Trust and the real estate appraiser and the real estate or the realtor associations did together. And nationwide, they found out that for every $1,000 in savings, that you would get $20,000 throughout the whole U.S. Value put on your house. Now, in Oregon, and the closer you are to Portland, you get $25,000 because we have a higher value for it. So in Arizona also, because they have a lot of light. So with that same example, if we had a 10 kilowatt system, we would get 40 kilowatt hours on average. They get 60 kilowatt hours on average, and some of the times they would get up to 80 kilowatt hours a day from their solar systems. So for a 10 kilowatt system, so pretty impressive stuff. Their incentives aren't as good as ours, which is kind of funny though. So then people say, 14 years, that seems like a long time. And, for me, doesn't sound, personally, it doesn't sound like it's a big deal, because you're never going to pay off your electrical system anyways. And if this adds value to your house, it is winning, and you're not having to outfork anything different. But, risk is different for different people. So are there any other options? Well, we just came out with this new one called the income-based solar, or solar within reach is what the ETO calls it. So if you make under $77,520 for a family of 4, and they have a schedule here of a bunch. I can actually show you what that is. Okay, so here's the PG. This is their standard rate here. You get a little bit more for Pacific Power. But the Solar Within Reach program is all here. So if you are a resident, one person in the house, if you make less than $54,240, and if you have a whole heap of kids, you can make up to $102,360. And then it's $1.50 a watt instead of the 30 cents a watt, and a maximum of $9,000 for that system. So we'll go back here and I'll show you the updated amount. Oops, sorry about that. Okay, so as we go through here, so if you make under that $77,520 for a family of 4, here's how this works out. So the system cost is all the same, right? That didn't change. But now the tax incentives did. So the ETO gives us $1.50 a watt versus 30 cents. So that gives us $8,520. Now we can actually go up to $9,000, which means that if we got a 6,000 watt system, we would fully max out both of these credits, and that would be the sweet spot for getting the system, or the maximum incentive for the system. So then we come back here at the state, and so the state has something, and I think their numbers were, like 8,300. So if you make under the 77,000, then you also automatically qualify for the state funding, which is $5,000. And so right there, that's almost 14 grand off your system. Then you get the federal ETO after the state and ETO funding. So the breakdown here is you get 8,500 from the ETO, you get 5,000 from the state, you get 1,277 from the federal, and your total system cost is 3,633 for nearly a 6 kilowatt system. And so your payoff for this would be about 4 years, and could potentially be, probably like 3 years because the 856 is a little low. But this is really incredible. Essentially you're getting your system for 50 cents a watt almost. Does that math work out? Let's see here. Let's see here. So if we take this, we go 3,633 divided by 5,680. Yeah, so you're getting your entire system cost for 64 cents a watt, which is cheaper than your solar panels by itself. So that's the question that I get a lot of times. Is like, oh, geez, if the labor costs $7,500, why don't I just do it myself? I could save $7,500. Well, the answer is you can't. Because if you don't use the labor and you don't hook up to the grid, you could still hook up to the grid, but if you don't do the labor, you don't get any incentives. So it's cheaper for you just to hire somebody to go do it, even if you're a solar contractor, which is kind of funny. So you could have your company do it for you, or you could potentially have a friend's company do it for you. And if they did it for you, then you would be able to get your system done. But essentially, it's more times than not, these numbers are actually, most people can fit under this category. So this is a really great incentive program for us. It's really exciting. So that's just something coming out here, guys. So that's the end of my slideshow for now. Go ahead and take a look at those resources in Moodle so that you can see. I could actually go over to Moodle real quick. Hold on for a second. So here in Moodle, I have one for this week, lecture resources. And so as you go through here, it has some job stuff, just like there's a couple positions there of what types of jobs you can get. There's the solar window. We have how does solar work, and then we had that really exciting video that showed like how the phosphorus and the boron and the valence shell electrons and all the stuff through there. And then I have some things over here is what's the most efficient systems, and then I have some polycrystalline, some monocrystalline thin film manufacturing, and then some kind of interesting ones that are on a very like hands-on, non-automated way of making solar systems, which is pretty cool. So anyways, guys, I hope that you had a good time. I'm going to be releasing another video here shortly to cover our next week's information. And then we have a meeting that's coming up on Friday that I'll send out here shortly of a Zoom meeting that you guys can tag into and check that out also. So have a good day. We'll talk to you soon.